Hello friends, in this video we are going to discuss about the band model of semiconductor. Sometimes it is also called the energy band model of semiconductors. As we know that this energy band model is nothing but a quantitative modeling of semiconductors. So quantitative modeling means we can see that during this modeling we will get an exact idea of the phenomena that will take place inside the semiconductor. Previously, the bond model of semiconductor was qualitative modeling. So from the qualitative modeling, that is the bond model, we have seen that we have got an rough idea about the phenomena of the semiconductors, but in the energy band modeling we'll get an exact idea of the phenomena that will happen inside the semiconductors. Generally, this band means it is a collection of energy. So this energy band model will give how many electrons are distributed over the range of energies at any given temperature K. So if we write, then we can say that this energy band model depicts that how electrons are distributed over the range of energies at any given temperature in Kelvin. So this is the outcome of the energy band model. So we can see from this energy band model there will be another outcome, is that from this energy band model we can also separate the bound electrons and the free electrons. Now, before going into the modeling using the energy band model, let us first know that this type of modeling, that is the energy band modeling, has some basic statements or facts or tenets on which the total modeling of the semiconductor depends. So if I write in this fashion that the basic statement or facts or tenets of energy band modeling. This is the first step of energy band modeling. First, we have to know what are the basic statements that are there in the energy band modeling. In the basic statement, that is the first statement, is about the allowed states, means about the allowed energy states. In the allowed energy state statement, it is written or it is given that electrons are allowed in certain energy states. It means that electrons cannot take energy of any number. They are allowed to take energy of certain values. That means we can say that now the electrons will have discrete value of energy. So this was the first statement. Next we'll go for the second statement of the allowed state. So the second statement says that of the allowed state that the electrons can take, electron always tends to occupy the lowest energy states available. This is the second statement of the allowed states. It means that if there are several allowed energy states, let us assume that these are allowed energy states. This is E1, this is E2, this is E3, this is E4, and this is E5. So there is an electron which can take these allowed energy values. So if this electron has to take the energy values from these allowed energy states, then this electron will always take the lower energy values if it is allowed. That's why it is said that of the allowed states, electron always tends to occupy the lowest energy states available. The second one is that now if we come to the third statement of the allowed energy states, then it states that no two electrons can occupy the same energy states. Actually, this third statement is called the Pauli's exclusion principle. And this Pauli's exclusion principle states that at any energy states E, suppose take a energy state E5. So in this E5 energy state, there will not be two electrons that can occupy the E5 energy states. That means in every energy states there will be a single electron. Now if we go for the second part of the basic statement, the second part of the basic statement states that how many allowed energy states are there. This is the second basic statement about the energy band modeling, and it also depicts how these energy states are distributed over energy. The physical significance of this statement is that from the second statement or basic statement of the energy band modeling of semiconductors, we can say that the second statement gives the distribution of allowed energy states over energy. This is the second most important part of the energy band modeling. And this distribution of allowed energy states is given by a function called NE. So this NE is the distribution function of the allowed energy states over the energy. In the later sections, we will see what will be this NE. Now, let us go to the third part of the basic statement. So, in the third part of the basic statement, it gives what fraction of allowed energy states are, or we can say rather than available energy state are occupied at any temperature capital T and energy capital E. So the third statement gives that how much fraction of the energy states, which energy states which are available, are occupied by the electrons at any given temperature capital T and energy E. So this fraction of the third statement is given by a function called FET. This is called the Fermi Dirac distribution function. So this Fermi Dirac distribution function gives how much fraction of the allowed energy states are occupied by the electrons. Later on in the upcoming lectures, we will see what is this Fermi Dirac distribution. Now let us discuss briefly about the allowed states. Now for this purpose, let us consider silicon isolated atom. Silicon isolated atoms. So for these silicon isolated atoms, if we find the available energy states, so we know that for silicon isolated atoms, we know the atomic number of silicon is 14. The atomic number of silicon gives the total number of electrons. That is, the total number of electron inside a silicon atom will be 14. So if I find the distribution of these electrons, 14 electrons, it will look like this: 1 S2, 2 S2, 2 P6, 3 S2 and 3 P2. So this is the electronic distribution of the silicon atom. As we know, 1 S2, 2 S2, 2 P6, 3 S2 and 3 P2. Now from the electronic distribution or electron distribution over the electronic state, we know that for a silicon atom, suppose this is a silicon atom and it is the nucleus of the silicon atom. Nucleus N, I am denoting N as nucleus. So this is the nucleus of the silicon atom, and we know that the 1s is the nearest to the nucleus. Then it will be 2s, then it will be 2p, and after that it will be 3s, and then it will be 3p orbitals. So in this way the orbitals are distributed. Now we know that in the 1s only 2 electron can be there. So there are 2 electronic states, energy states, and these 2 energy states are in the 1s. In the 2s, similarly we know that there can be 2 energy states. Similarly for the 2p, we know that there will be 6 energy states maximum that can occupied by an electron. Similarly for the 3s orbital, we know there are 2 energy states, and for the 3p orbital we know that there will be 6 energy states are there this way. Now in the 1s there are 2 electrons, so 2 states will be occupied by the electrons. So in the 2s there are 2 energy states, so these 2 energy states will also be occupied. Similarly the 6 energy state in the 2p orbital will also be occupied. So in the 3s it will be also occupied. So now the total number of electrons is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 2 is remaining, but in the 3p there is 6 energy states, but we have only 2 electrons remaining. So out of the 6, 2 energy states will be occupied by the electrons and 4 energy states will be vacant. From this case we can also say that the valency of the silicon atom is 4, because there are 4 vacant energy states at the 3p orbital. Now let us put an isolated atom at one place. For that, let us draw a diagram like this. Let us put an isolated atom here. There is a silicon atom, and there is also an silicon atom I am placing here. But this silicon atom is in static position, that is not moving, it is fixed. It is fixed. And this atom is moving, suppose it is moving in this direction. Now this silicon atom which is moving, I am naming it as silicon atom number 1, and I am naming this silicon atom as a silicon atom. Now when the silicon atom A and 1 will be far away from each other, then there will be no interaction of the orbital energies with each other. For the silicon atom 1, we know that the first orbital will be 1s orbital. The second orbital will be 2s orbital, and the third orbital will be 2p orbital, and the fourth orbital would be 3s orbital, and next we will have the 3p orbital. So we know that the 1s orbital energy state will be occupied in this way. 2s orbital energy state will also be occupied in this way. 2p orbital energy state will be 6, and all of them will be occupied by the electron. Similarly, 3s energy state will be occupied, and in the 3p there will be 6 energy states in this way, and out of them only 2 would be occupied. Now let us assume that we are bringing this atom 1 closer to A. So as this silicon atom number 1 is coming closer to the silicon atom number B or A, so the interaction of the orbital will start. So the first orbital that will interact will be the 3p, then it will be 3s. So if we take, as we take the silicon atom number 1 closer to the silicon atom number A, the 3p and 3s orbital of the both atom will interact with each other, and what will happen? They will start interacting. That means the 3p of the silicon atom A will merge with the 3p orbital of the silicon atom 1. So now we can see that in the 3p orbital there will be a 3p orbital, and this 3p orbital will now occupied by 4 electrons, and out of these 4 electrons 2 of them will be similar, because this is also a silicon atom and this is also a silicon atom. So we can say that in the 3p orbital there will be now 4 electrons, out of them 2 of them will be similar. So according to the basic statement of the energy band model, we know that no two similar electrons can occupy a single energy state. That's why these 3p energy states will now be divided or splitted into two parts, and similarly the 3s energy state will also be divided into two parts, because according to the Pauli's exclusion principle, this in these energy states not two electrons cannot reside. So in the 3s, same type of electrons are coming from silicon atom A and silicon atom 2. So to follow the Pauli's exclusion principle, the 3s and the 3p energy level are divided or splitted, and they will form in this fashion. Now if we bring more closer, then we can see that the energy levels will be, or the orbitals will be splitted in this fashion. If we bring more closer, so ultimately they will bring split in this fashion, and the total orbital will look like this. Now in this case we have seen that there are two atoms, and for the two atoms we can say that there are 6 energy states. For this one atom, there are 6 energy states in the 3p energy level, and out of the 6 states, 2 states has been occupied by the electrons, so the total number of electrons at the 3p orbital is 2 electrons. Similarly, for the 3 states, 3s orbital, there is 2 states and 2 electrons. Now we can say that in this region, in this region, so before going into this region, now let us suppose we have n number of silicon atoms. That means we are moving n number of silicon atoms from different directions. So at that case, there will be 6n number of states in the 3p because there are n number of atoms. Similarly, there will be 2n number of electrons. Similarly, in the 3s, there will be 2n number of states and 2n number of electrons. So in this dotted region, we can say that within this region, there will be total 6n plus 2n means 6n plus 2n number of energy states and 2n plus 2n number of electrons. So within this region, there will be total 18 number of states. So if we draw, there will be 18 number of states like this, 18 number of states in this fashion. I am not drawing all those, I am drawing few of the energy states. So in this way, there will be 18 number of states, and out of which 4n number of electrons will be there. After that, this total 18 number of states will be equally divided by same number, that means 4n number of states will go in the this part and 4n number will come at this part. Now we have seen in the basic statement that the electrons always tend to occupy the minimum available energies. So these lower energy 4n states are the available minimum energy. So all the 4n electrons will come in the lower energy states, and here there will be 0 electrons. Now we can see that in this part there are 4n number of states and 0 number of electrons, and in the lower energy state there are 4n number of energy states and 4n number of electrons. Now suppose if I draw a line like this at this position, if I draw a line at this position, then this line will cut the orbitals at this point, So if I take these 4 points like this here, suppose I am taking only those points. Now if I take these 4 points and if I extend them and if I replace them with a line, then they will look at this. So I have replaced the points with a line. Now we can see that within this region there are foreign number of energy states, and all the foreign energy states are occupied by electrons, so there are foreign number of electrons. Similarly, in the above region there is foreign number of states and zero number of electrons, and in between this region there is no energy states, because there is no energy states here. This region or this gap is called the energy gap, and this thing is called the conduction band CB, or the lower foreign number of energy states is called the valence band. So if we draw this structure in a freshly method, we can write like in the above part, this is the conduction band, in short we'll say CB, and in this conduction band there were foreign number of states are there but zero number of electrons. Similarly, in this lower region there will be foreign number of states, but all of them will be occupied by foreign electrons, so this is valence band, because all the valence electrons are here right now, so this is called the valence band. In short it's called as VB, and there will be foreign number of states like this fashion. There will be so many states, energy states. So many energy states will be there like this fashion. Similarly, in the valence band, there will be so many energy states. But all of the energy states will be occupied by this foreign number of electrons. And this gap where there is no energy states is called the EG, or it is called energy band gap. So this is called the energy band diagram of semiconductors, and the maximum energy value that is present in the valence band, this is denoted by EV, and the minimum energy value of the conduction band is denoted by EC. So this is the EC and this is EV, and this total structure is called the energy band diagram of the semiconductor. Another important thing is that if we go to the previous diagram, in this diagram we can see in the x-axis, we have plotted the atomic displacement, that is the distance between the two atoms A and 1, and at this point we have taken the points. These green points has been taken at this line. So That means now this silicon atom is right here at this position. Then we are taking these 4 points. So the distance is this one between these two atoms is called the interatomic displacement. Interatomic displacement is the distance between the two atoms when or where the points has been taken. We cannot call this distance as an interatomic displacement. Only we can say that this distance is the interatomic displacement or interatomic distance. This is all about the energy band model. Thank you.